Yeah, this is Dr. J. Mohan from EC Department of Institute of Aeronautical Engineering. I'm going to talk about the system in the third section, the subject of signals and stochastic processing. Last class, we studied for the system. System is defined as entity that act on input signal and transfer it into the output signal. And the system is the elements like discrete elements of inductor, resistor and capacitor are in the electronic devices. It's a diode, transistor and FET devices. So those devices going to combine together, we make it for the function block. That will be represented as a system. It's taking the input, it's producing the output based on which kind of input we are going to give. It will be going to produce the same kind of output. For here, the example I take for the system, continuous time signal. That means it represents a time-based signal that is called for the x of t. We pass for the system, the functional block is represented as a s. We passed, then produce the output also is represented as a y of t. We given for the x of t, its produced output is represented as y of t. That will be, we write for the system function, yes, what we are going to represent here, yes, into x of t we given for the input, or we represent for the y of t is equal to t into x of t. Okay, so here instead of s we may use for the capital letter T also. This is represented as a system. Next, we studied for the two type of system. One is continuous time signal system, another one is a discrete time signal system. What we are going to given the input here. For the input is a continuous time signal. That's why its system is called for the continuous time system. Our best example is amplifier. Its produce the output is C of t equal to T R of t. Then discrete time system. It's taking the input of discrete time signal. It's produce the output also discrete time output. So we given for the input is R of n. This is discrete time signal input. Its produce the output is represented as C of n. For this one is best example is microprocessor. C of n is equal to T R of n. This is the way we may represent as a mathematical model of system output. So at the same time, we studied for the classification of systems. What are the classification? Linear and non-linear system, time variant and time invariant system. Linear time invariant system as well as a linear time variant system. Static and dynamic system, causal and non-causal system, invertible and non-invertible system, stable and unstable system we studied. Last class, we discussed for the linear and non-linear system, time variant and invariant system, linear time variant and linear time invariant system, static and dynamic system. This class we go for the causal and non-causal, time variable and non-invariable system and stable and unstable system. So first we go for the causal and non-causal system. What is the meaning of causal? The system whose output or response at any instant t depends only on the present and past value of input, but not in the future value of input, is called for the causal system. For example, we have for the input, that is input x of t is equal to u of t. So the x of t is equal to u of t. We know u of t is represented as a unit signal that is equal to 1 when n, that is t is greater than or equal to 0, 0 when t is less than 0. That means here what will be going to have for the input in the x of t? The x of t consists of X of t consists of u of t, that is 0. When the 0 is equal to 1 for the u of t, in the case 1, it is represented as a 1. This is 1 as a positive side. This is 2, it's represented as a 1. It will be continued. For this negative side, all values are 0. This means this 0 is called for the present value. Then this 1, 2, 3 all are past value. This kind of signal we call for the causal signal. If the signal is present for the present and past value of input, then the system is called for the causal system. Otherwise, the system is represented as a non-causal system. The best example is unit impulse signal. Next, we go the causal system. The output or response does not begin before the input signal is applied. This means if the system, you take for the system is represented as I represent as a capital letter T, the square bracket I given for the x of t. This input is x of t, y output is going to produce for the y of t. Now this is equal to t into x of t, we write for the system function. So if not giving any input of here in the system does not provide the output. That kind of system also is represented as a causal system. The causal system is also called non-anticipated system. Why? Because of when you are going to give the input, then only the system is going to get to perform. That kind of system is represented as a causal system. Otherwise, we call for the non-anticipated system. The causal system are real-time system and they can be physically realized for the causal system. So physically realized in the sense it's made for the electronic circuits that will be represented as physically we may represent for the circuit. That kind of system is represented as a causal system. For example, here I take for h of t is equal to 0. This h of t, how it became? The h of t is represented as a linear time invariant system we studied. We given for the input as x of t is represented as a del of t we given, that is impulse signal. The system performance is produced, the output is represented as a y of t. This y of t we call for the t into x of t. This value, what the t value is present, that is del of t, we can substitute. This 2 is represented as a t into del of t, we call for the h of t. Okay. So this h of t, that is a system performance. The h of t is called for the system performance response. This h of t equal to 0 when t less than value equal to 0 for the continuous time system. That means the h of t, it's going to active for only the h of t active for only t is greater than or equal to 0. If t less than 0, that is t less than 0, it's represented as 0. There is no signal present for the only left side. That means the signal is present for the minus into plus into the 0 to, that is 0 to minus infinity, there is no signal, it's represented as 0. That kind of signal we call for the causal signal in the continuous time system. Then discrete time system also is represented as h of n is equal to 0 when n less than 0. That means negative side of sample, all is represented as 0. For the case, a resistor is an example of continuous time signal, continuous time causal system. Resistors only pass when the input is present, then it's going to produce the output. That system is called for the causal system. Example, we take for the some example. So y of t is equal to x t minus of 3 plus 3 x of t, and y of t is equal to t x of t. Then y of n equal to x n minus of 1 plus x n. Y of n equal to n x of n. We will see whether the signal, the system signal input, the system produce the output is y of t, whether this is represented as a causal or not. Next case, non-causal signal. A system whose output response at any time of instant t depends upon the future value of the input. is called non-causal signal, non-causal system. So what is the future value in the sense? If take for the h of t, this value equal to 1 when t greater than or equal to 0. 0 is t less than value of 0. This means these are the values. That means that t less than 0, this the negative value is called for the future values. So if the system is produced, the output is represented as a future value, then the system is called for the non-causal system. For example, we take for the previous one. See here. So here is represented as a y of t is equal to x of t minus of 3 plus 3x of t. We take for this as an example. For in the case of causal as well as of non-causal case. Now I should apply for the value of t. What will be going to happen? So here t minus 3 is there. That means what is it? T minus 3? It's represented as a past values. Is represented as a t minus 3 is called for the past value. Because of t minus 3 equal to 0, t equal to 3. Because of we get for the positive value here. And this one you take for here t, that t is represented as 0 because of this is present for the present value. So that's why this system output y of t is represented as a causal. Next, we take for here y of t, this one another example, y of t that is equal to x of t into t. That is y of t is equal to t into x of t. Now you should apply for the minus value to here. That is t equal to minus 1. What will be happen? Y of minus 1 is equal to minus t x of minus t. Then t equal to 0. Y of 0 is equal to 0 into x of 0. Then t equal to 1. Y of 1 equal to 1 into x of 1. So this system, what is it? The y of t is equal to t x of t. This system it will be performed for all the inputs. What is it? This is a past value input, is a present future value inputs. All inputs it's getting to perform. So that's why the system is represented as a non-causal system. That will be I represent here. A system whose output response at any time it depends upon the future value of input is called non-causal system. Then it's mathematically represented as a h of t. H of t equal to is not equal to 0 when t less than value of 0. We may represent this h of t is not equal to 0 when t less than the value. So that is, this means is a future values of input. The non-causal system can generate an output before the input is given. Before the input is given, output is getting to generate. For example, CMOS circuits. What it will be going to do? It's going to work for the minus voltage, minus current also. That is minus I voltage also. Like that circuit, it's represented as a non-causal system response. So most of the memory devices are going to design based on the non-causal system. This system also known as a anticipative system. The non-causal system do not exist in real time. Also, the system are not physically realizable. We need to make force to physically realizable. For the case, image processing system are example of non-causal systems. This is represented as a non-causal, causal as well as a non-causal. For example, non-causal, here we take y of t is equal to x of t plus 3 plus 2x of t. You take here, what will be happen for this case? T plus 3, 3 is going to start at for the initial value 0. Then t is equal to minus of 3. Now what we are getting? We get for the minus value of the t. So this, if we get for the minus value in the sense, it will be represented as a non-causal system state. Next, we take for here. Here is doesn't have a problem. It's going to present for the present values. But you take to here and here. It's going to produce for the output of future values. Then you take for here. This is x of n. X of n into 3n. You can substitute n equal to minus values of 1. N equal to minus 2. Then n equal to 0. Like that one you may substitute for here. So y of 0 is equal to x of minus 1. See, here we get for the minus value. Plus 3 x of 3 minus 1. Here also minus. So that's why this system is going to satisfy for the non-causal state. Then after you take for here, and the y of n equal to x square n plus 2 x n plus of 1. So here is plus is there. That's why it will be n plus of 1 equal to 0, n equal to minus of 1. It started for the minus direction. So that's why it's represented as a future values. Okay. So then when the future value is going to happen, the system produces the output is represented as a non-causal state. Here you take for the some causal and non-causal state. Here I am going to explain for some sequence. So y of t is equal to x square of t plus x of t minus 3. Y of t is equal to x of 3 minus t plus x of t minus 2. Y of n equal to x of 2n. Then y of n equal to sine of x of n. First we take for the first sum, this one. So y of t is equal to x square of t plus x of t minus 3. But this system, whether we need to prove whether the causal or not. The causal of the system gives the system can be determined by considering the different value of t we need to substitute. Then t equal to 0, you substitute for the y of 0, x square of 0 plus x of minus 3. Okay, please note down for here x of minus 3. Then t equal to minus 2, y of minus 2, x square of minus 2, x of t minus 3, that is t equal to 2, then that's why it will be the minus 5. Then t equal to 2, like that one, y of 2, x square of 2 plus x of minus 1. So, we given for the past, present and future value. Okay, past, present and this is a past, present, future value we given. It's the all value of t, the output depends only on the present and past values of the input. Then the system is called for the causal system. Like that one, we may represent for all the cases. For here, you take for another example, y of n equal to x of 3n. We substitute for the 0, x of n equal to minus 1, n equal to plus 1, n equal to 2. That is a present, past, future value we substitute. It's going to give for the 0 in the sense x of 0, minus 1 is in the sense x of minus 3, this is 1 is x of 3, this is 2 is represented as 6. Now what will be happen? We given for the positive as well as of negative value of n, the output of system depends upon the future value also of the input. Therefore, the system is called for the non-causal system. Like this one, you take for the sine signal. And the output of the system, we may give for the different type of input samples in the discrete levels. 0, minus 3, plus 3. Then this is y of 0, y of minus 3, y of 3. That is sine of x of 0, sine of x of minus 3, sine of plus 3. Now you can see for all the case what we are going to given, based on that one it will be going to produce the output. So that's why the system is represented as a causal system. Next we go for the invertible and non-invertible system. First, invertible system. If the system has a unique relationship between the input and output, the system is called for the invertible system. Now I take for the system. First one is represented as x of t. I'm going to x of t or x of n. Whether you can give for the continuous time signal or discrete time signal. Depends upon the case system is getting to vary. Now I'm going to do for the system. The system it's produce a performance that is represented as h of t is equal to t into the square bracket of what we are going to given per year del of t you make given. The system performance generally we call for the h of t. That's why I represent as a square bracket of t. Its produced output is y of t. If you are going to give for the x of n, it's produced for the y of n. Then again, what I am doing, I make to use for the invertible. Then I take for the inverse of this system, that is called for the invertible. It's going to produce same kind of output as a input. What we are going to given here, same it's going to produce the output. This kind of system is called for the invertible system. Or if you are going to discrete time signal as x of n, the output is represented as a y of n of system function output. You take for the inverse, it's produce the output is x of n. This kind of system is called for the invertible system. Here I take for the example, x of t is equal to t inverse of y of t is equal to t inverse of t x of t. This y of t is equal to, I write for this one, t x of t for the continuous time system. You take for the discrete case, x of n equal to t inverse of y of n is equal to t inverse of t x of n. This y of n is equal to this one. So this is a performance of first case. This is a performance of second case. If you do for simultaneously for all, we get it for the input as a x of n. So this kind of system is represented as a discrete invertible system. Next, non-invertible system. A system is said to be non-invertible system if the system does not have a unique relationship between the input and output. What we are going to given the input of, you take this diagram. Here we may give for the continuous time signal or discrete time signal. So x of t as well as well. You do for the system performance, that is t, its produced output is equal to y of t. Then we may take for the inverse, but it's not like the input. It's going to change the character, whether it's a time is getting to changed or amplitude is getting to changed. This kind of system is represented as a non-invertible system. We take for the example x of t. We need to produce the output for system as well as the inverse system. The output is represented as what we are going to given for the x of t is received for the x of t. If not, only is represented as a non-invertible system. You take here, first you take for the inverse the output, okay, then you pass for the system response t x of t. So it's not getting for the x of t. So it's not getting the x of t of this system performance. It's called for the continuous time non-invertible system. You take for the discrete case, x of n is not equal to t inverse of t x of n. For this system is represented as a non-invertible system of discrete time signal. For example, you take for here y of t equal to 5x of t. Now x of t equal to I given for the 3. Then the output of the system is represented as a 5 into 3. This x of t is equal to 3. That's why it's 15. Now I give for the minus 3. X of t is represented as a minus. Its produced output is equal to 5 into minus 3. Where the x of t is there, you substitute for the minus 3. Then we get for the minus of 15. For you compare with these two in output of the system, the different input we are going to given, there is a different output. Therefore, the system is invertible system. At the same time, to take for the another example, y of t is equal to 5x square of t. Now, I given the input as x of t is equal to 5. The output is equal to y of t equal to 5 into x square. What is that? Is represented as a 5 square. Is represent 125. We get for the output as a 125. Now, I change the sign value of your x of t as same input minus of 5. The output is equal to 125. Now, what will be happen? Both the inputs are similar. So, the given system, if you are going to give for the any different input, it's produced for the same output. In the system is called for the non-invertible system. This is the example of invertible, non-invertible cases. Next case, we go for the stable and unstable system. First, we go for the stable or BIBO stable system. BIBO in the sense bounded input and bounded output. If the system is taking for the bounded input, the output also is represented as a bounded. Then the system is called for the stable system. For the definition of stable system is, a system is said to be bounded input and bounded output, that is called for BIBO. The system is represented as a stable system or simply stable system. If and only if every bounded input produces a bounded output, the output of the stable system does not change unreasonable. For here, I take the example. Here I given for the bounded input. What the bounded? I started for the 0. The system is going to complete it for the some duration of your t. It's in the signal. This signal I am going to give for the input of the stable system. It's produced the bounded value. What the bounded value? Where we are going to start at, where the signal is stopped in the input, same like that one, it will be going to stop here. Here is started, 0 is started, the end is represented here. So that means what the bounded input you are going to present, the same bounded output you are going to get. This kind of system is represented as a stable system. The stable system or stability of the system can be determined for impulse response of the system. The impulse response of the system, nothing but the output of the system for unit impulse inputs. Let us input we take for the bounded signal. That bounded signal I take for the mod, whether it's represented as a minus direction or plus direction. Anything is going to present for the your time interval as a continuous time signal. Mod of x of t, whether it's represented as a minus direction of infinity of 0 up to plus direction of our t is going to present. So it's represented as I make two bounded cases. So that's why we take all into the mod value. The x is represented as a x of t of mod. It's getting for the some constant k of x, that is a bounded constant, is represented as a positive real number, is lesser than of infinity. What we are going to get? That value is represented as that bounded value is as an infinity for both minus infinity of t to plus infinity of t. Now, k of x is represented as a positive real number. Then the output also it's going to produce same like that one. Mod of y of t less than of ky less than of infinity. This is represented as a bounded input. This is represented as a bounded output. The k is represented as a positive constant of real number, not we get for the imaginary cases. That is the output of the system y of t is also bounded. Then the system is called for the BIBO, stable, bounded input, bounded output, stable. Next we go for the unstable system. If a system does not satisfy for the BIBO stability condition, then the system is called for the unstable system. For bounded input, if you are going to give, it is not necessary that unstable the system produces a bounded output. If you are going to give the bounded input, the system performance is, after system performance is produce the output is not a bounded. That kind of system is represented as a unstable system. We can say that the system is unstable even if one bounded input generated an unbounded case. For here example, I take for the same kind of system, same kind of input. The system is represented as an unstable system. The input is started 0, it's finished for the some duration. It started 0, finished for the some duration. The output, it started 0, it's not possible to finish for the some duration. Suppose it's going to complete it for the input response is 5. It's maybe it's increase 6 also or 3 also is going to stop. So this kind of system is called for the unstable system. But a stable system, if we stop 5 for the input, here also is represented as a 5. Okay, this is the difference between the stable as well as an unstable system. For example, we take whether the system is stable or not when the input is represented as a t plus 7 u of t. The system performance y of t is equal to t plus 7 u of t. Now I take for the y of t, t plus 7 u of t. What is that u of t? We know that t is present, that is u of t is 1 when t is present greater than 0. 0 is represented as a t is less than of 0. The one amplitude is present, that's why it will be greater than 0. So that's why I simplified for the equation as y of t is equal to t plus 7 into multiplication of 1. This whatever maybe if you want to multiply 1, you will get for the same amount of signal. So that the condition I write for the t is greater than 0. For the t greater than 0, greater than infinitive, then y of t is also is represented as infinitive. Thus the output system is increased without any bound. Therefore the system is known as unstable system. Next case. Up to this much I am going to conclude it for the system response. I covered for the entire 7 system. So what are the system we studied? We studied for the linear and non-linear system, time variant and time invariant system, then linear time variant and linear time invariant system, static and dynamic system, causal and non-causal system, invertible and non-invertible system, stable and unstable system. Up to this much, I'm going to conclude this section. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.